Next up, we have Eric Bodden and Dominic Schubert, who are going to, he's showing up as a name here. Eric Bodden and Philip Schubert as presenters for the Soot and Phasar systems. Since both of these systems are relatively closely related, yet rather different systems, we are combining their presentations and we'll have a joint Q&A session afterwards.
Yes, hello, my name is Eric Bodden, and together with Philip Schubert, we are today presenting you our static analysis frameworks, Soot and Phasar. Today, we want to talk a little bit about what we do and who else is behind these frameworks. And then we are going to present both frameworks, Soot and Phasar, side by side, talking about the general functionality, how they work internally, how you can use them as somebody from the community, and also how we want to develop these frameworks further. And you are most welcome to contribute to further development of both Soot and Phasar. So my name is Eric Bodden. I'm a professor for software engineering at Paderborn University, and also I'm heading the group on software engineering and IT security at Fraunhofer IEM, which is also located at Paderborn. And I'm here together with Philip.
Yeah, hi. Welcome also from my side. My name is Philip Schubert. I'm a PhD student of Eric's software engineering group at the Heinz-Nixdorf Institute and the Fraunhofer IEM.
And these two institutes, they sit right next side by side in Paderborn. And the main difference is basically that on the right-hand side at the Heinz-Nixdorf Institute, we're doing a bit more basic research. So here we research mostly novel algorithms and data structures when it comes to code analysis. And at Fraunhofer IEM, we are really focused on turning these tools into production-ready use and trying them out together with industrial customers. So let me first talk a little bit about the Soot framework. So Soot was actually established already in 1999 by the Sable Research Group at McGill University, and that is a kind of long time ago, right? So I actually finished my high school degree back then, and if you want to remember what 1999 looks like, that's about it. Yeah, a little different from today. So 1999 was when Soot was first conceived, and then it really became well known at PLDI 2003 when there was the first larger tutorial about it. And this here is still one of the original slides from back then. So as you can see here, back then they were still talking about compilers and programming languages such as Small Eiffel and Java and so on, which were all being transformed to Java class files. And then the idea behind Soot was that you would be able to analyze and transform and optimize these class files. So it was a lot about ahead of time optimization. And then you could load these optimized and potentially attributed class files into sometimes even specialized virtual machines. That is not the main use of Soot anymore. I'm still going to be talking about how this changed. But back then, that was sort of the game. Today, we have support not only for the Java platform, but also for Android. This has been there since 2011. And Soot really has a huge user base. So the Soot papers have more than 1,300 citations. And on GitHub, there are more than 1,400 people who apparently like the project. We have some commercial deployments. For instance, it's running as part of the largest app stores in combination with Floatroid that I will still be talking about. And it's open sourced under the LGPL license. So anybody can use it, but also anybody who is directly modifying Soot's code is asked to contribute back these changes to the open source project. Philip.
Yeah, all right. So in 2016, we developed the Phasar framework within the SFB 901, the Collaborative Research Center on the Flight Computing. We've really wished to analyze C and C++ code, and we felt that there is not much out there which you could use for static data flow analysis, especially, which is really why we developed Phasar in the first place. And at the beginning, we pretty much implemented some IFDS IDE solvers, which allow inter-procedural data flow analysis, and then over time we built basically the framework around those solvers. We presented then the framework at the PLDI tutorial in 2018. The Phasar framework again allows for static data flow analysis, and it supports LLVM IR. In particular, C and C++, you could analyze with the Phasar framework by using the Clang compiler to produce the intermediate representation. And we nowadays also have a growing user base. We have more than 390 people who like the project on GitHub. We also have some commercial engagement by now, and Phasar is available under the very permissive MIT license. So you can pretty much use Phasar for any use case that you might have.
Thanks, Philip. Yeah, and as you will see later, a lot of the components in Phasar are really modeled to mirror some of those that we have in Soot. So we really try to provide a similar functionality here for C and C++. And one of our key motivators for doing this is also that we saw a lot of demand for C and C++ analysis in the last few years. If you want to play around with these frameworks, so for Soot, you would go to sootoss.org. It's a relatively new domain that we reserved for the tool. We have some usage documentation in the wiki. I have to say it's not always up to date. We're actually always also looking for volunteers to try out the documentation, and please let us know if something is not working for you. You can now very easily integrate all of this using Maven, so it's very easily built and included through this. We do support current Java bytecode by now, so we recently added support not just for Java 9, but up to version 14 actually. There may still a few bugs in this area, but most of the support should actually work. We also have some limited support for analyzing source code directly, but the source code front end right now is not very stable. We're currently working on this. But my current recommendation would still be, if you can, do compile source code to bytecode and analyze that instead. And then, yeah, Soot has a lot of support for code analysis, but also code transformation. So if you want, you can also instrument and optimize Java or Android bytecode this way. Philip?
All right, so for the Phasar framework, you probably wish to go to phasar.org. It's a small blog, really, where we provide useful information on the Phasar framework. And from time to time, we also publish some smaller useful articles on Phasar and how it can be used. You will find the source code on GitHub in our secure software engineering group /Phasar. There really you find all of Phasar source code. And it's also accompanied by the documentation. So we make use of the GitHub wiki, where you can find how to install it, how to obtain it, first of all, and also what you can do with it. As Eric mentioned for Soot, I mean, it pretty much also holds for Phasar. So documentation is sometimes a bit outdated. So please let us know if something doesn't work for you. We try to improve on that, of course. The Phasar project itself is built via CMake, similar to LLVM, and that's also why it integrates very well with LLVM and also with other C++ related projects. So it makes it really nice and easy to use, really. So again, it supports the C-like languages, including C and C++. You can, for instance, use the Clang compiler for that. But you could also really use every other compiler that targets the LLVM intermediate representation. And Phasar allows for static analysis, data flow analysis, so you can analyze the code, and also provides some capabilities to transform the intermediate representation.
Great. There are also some foundational papers about both frameworks. So the ones about Soot, they also date back to '99. So there's the famous CASCON paper, which has been cited many times. It actually won also a CASCON 10 years best paper award by now. So this is the first introductory paper on Soot. And then sometime later, actually, Patrick Lamb and myself and a few others, we wrote a retrospective about the Soot framework, so how it evolved over time. And I think that's also an interesting read, gives you a different perspective on things. And a paper that I also often give to my students and PhD students is a technical report that you can download from the Sable website. It's on the Gimple IR and explains how it is actually being produced within Soot and what its properties are. And if you find yourself manipulating Gimple, that can be actually very useful to get some background information about. Philip?
Yeah, for the Phasar framework, you probably wish to have a look at the PLDI tutorial we gave in 2018. You can find all of its materials on phasar.org. We also published a full tool paper on the Phasar framework at TACAS 2019. That might also be very interesting for you, I guess, if you wish to get familiar with the overall framework and in its design. And also we published a small paper at SOAP 2019, Know Your Analysis, how instrumentation aids understanding static analysis. So apparently, as it turns out, static analysis can be quite hard, especially as static analysis is usually not just one analysis, but many analyses really that are interleaving each other. And so we really used instrumentation to get some new insights and to be able to debug analyses and to optimize them. So that might also be very interesting for you.
Okay, what you see here are some of the internals that both frameworks support. And yeah, let me go through the different kinds of analyses first for Soot. So both frameworks have a 3-address code intermediate representation. So that means all the program statements are broken down into really simple atomic statements that really only perform a single operation at a time. And in Soot, this representation is called Gimple, and it's relatively high level. So to a large extent, it actually looks like Java source code, except that it doesn't have loop constructs, and instead it has gotos. And then based on Gimple, you can do a lot of analyses and transformations. So in particular, you can do call graph analysis. And there are a number of standard algorithms that Soot all supports, like CHA, RTA, VTA. Then you can also do a standard Anderson-style inclusion-based pointer analysis and use that to create a call graph. And what's also interesting and important for Android analysis that Soot directly integrates with FlowDroid. So FlowDroid is actually a taint analysis tool that we built for Android, but it is also capable of constructing a reasonably sound call graph for Android applications. So we have that support as well. And when it comes to points to analysis, like I said, there's an Anderson-style analysis, but back in 2006, we also got contributed refinement-based context-sensitive pointer analysis. So that lets you refine certain pointer information for individual pointers. That can sometimes be pretty useful. And we ourselves also published a pointer analysis algorithm called Boomerang, which is flow sensitive and context sensitive to a very large extent. And it's also demand driven, which makes it relatively efficient. And that can also be used in combination with Soot. Then on the bottom of the slide, you see a number of interprocedural data flow solvers that can all be used in combination with Soot. So These don't come with Soot directly. You have to download a separate package, but that's about it. So they link automatically with Soot and they're very easy to use. For instance, we have an implementation called Heros, which gives you an IFDS IDE implementation. We have FlowDroid as a taint analysis. And we have Ideal, which is basically an implementation of the IFDS framework that fully automatically integrates Boomerang, though, to automatically resolve pointers in a very precise way. So basically, using Ideal, you can model data flow problems very easily without having to worry at all about pointers and aliasing. So this is all taken care of for you automatically. Then the latest support that we have is synchronized pushdown systems. So this is an evolution of Ideal, I would say, which uses a special way of pushdown systems to actually gain additional speed and precision. I'll still be talking about this on the next slide. Philip?
Okay. Also, as you can see on this slide, Phasar is modeled in a very similar way to Soot. So as intermediate representation, we are using LLVM IR. It's much more low level though than Gimple. But on the other hand, it is in SSA form, which makes it also quite handy to use for performing data flow analysis on. For the most part, the Phasar framework is implemented in a very generic way using templates and interfaces, which also allows us potentially to analyze other IRs. Maybe also someone wishes to analyze IRs from GCC. That would also be perfectly fine. So you would only really need to implement the language-specific parts, for instance, the inter-procedural control flow graph, and then you can write your own data flow analysis for other IRs. In terms of call graphs, we pretty much have the same. For the points-to analysis, we are currently making use of LLVM's points-to infrastructure, which is unfortunately not known to be very precise, but we are currently working on that. So we plan to integrate some demand-driven analyses using synchronized push-on systems to obtain much more precise points to information, but this is currently work in progress. In terms of data flow solvers, we also have an IFDS and IDE solver implementation. We have call strings implementation, so also the inter-procedural version of the monotone framework. And we also have the weighted push-on systems by using the Wali open nested word automaton library in C++.
Yeah, and just to give you a brief hint about what these synchronized pushdown systems are about, so basically they implement combined backward analysis, which you see here at these red arrows, and forward analysis, which are these green arrows. And what's important about it is that it models actually a fully context-sensitive problem and a fully field-sensitive problem. With some limitations. So normally this is an undecidable problem. So there are some situations where we have to cut some corners, but we were able to show empirically that normally these situations where you do need to approximate, they don't really arise very often in practice. So in practice, it's actually a very precise and also efficient framework. If you want to read more about it, there's a PhD thesis by Johannes Späth about it, which I cite here, and also a paper which we recently had at Popple. And also there will be a talk by these three people, including Tom Reps, on Saturday here at PLDI, which I also encourage you to take a look at. They also experimented a bit with this implementation. Yeah, then if you want to include these tools in your project, this is how it works. So Soot basically provides these functionalities that I talked about. And you can very easily include it using Maven, Gradle, SBT, and so on. You can use it typically as a command line tool. There are some IDE integrations, but we don't officially support them. And there's a mailing list and an issue tracker that people frequently use to notify us about questions or problems they're having with Soot.
Phasar, on the other hand, is organized as a monorepository. So once you clone it from GitHub, you obtain everything pretty much. Again, it's organized using CMake. Therefore, that means it allows usages such as libraries. So you can write your own tools, really, that use Phasar as a library, where you can just take the parts that you're interested in. You can, for instance, use the call graph functionalities if you're interested in that, or only use the points to implementations that are there. You can also use Phasar plugins. So Phasar is pluggable. So you can write your own plugins, which you then hand over to Phasar, and it will execute them on the target code. And there also exists a command line tool, which is called Phasar-LLVM, which you can use, and you can access all of Phasar's functionalities by using that command line tool. If you need any help, we have a Slack channel where a lot of bright minds are currently included. If you wish to be added to the Slack channel, just drop me an email and we'll add you.
Yeah, then one project I still want to talk about, it's called Future Soot. It's a project funded by the DFG, and its purpose you can basically see on the right-hand side. So Soot is basically a framework that evolved over 20 years, and lots of bits and pieces have been edited over time. But the architecture already had some problems in the first place, and all this adding up didn't make it any better. And so now the purpose of this project is basically to come up with a very clean new design that still gives you the same functionality, but with lots of better software engineering properties like modularity, better testability, and so on. The IR will mostly stay the same. We are doing some minor changes, but yeah, it's still going to be a variant of Soot. We hope to be able to release a first version of this probably around the end of the year. And we are also going to be conducting a little workshop with interested stakeholders in the next few weeks, probably. So if you're interested in contributing to this or learning more about the project, please let us know, and we are happy to include you.
So what are our future plans for the Phasar framework? Old dogs, new tricks. So what we are currently doing is we improve on the synchronized push-down system solvers. We try to add support for strong updates. That's something which currently does not work in the existing implementation for Java. We are also going to fine-tune all the algorithms and the technical details. Then, unfortunately, if you have to analyze C and C++ codes, this usually comes with some additional difficulties that you need to overcome. So we are also now trying to solve some C++ specific problems. And we plan to evaluate the synchronized push-down systems on larger pieces of production software as well. For the technical improvements, sorry, Eric, that was one slide too far. Yeah, no problem. For the technical improvements, we already currently completely revised the analysis model to make it more usable, easier to use, especially for beginners. And now we are currently also working on performance improvements, because for some real-world applications that we are currently analyzing using Phasar, it turns out to have some scalability issues, especially if you have analyses that really try to find interesting properties. There also we have to fine-tune a bit to make it reasonably scalable.
Thanks. So just to summarize, so static analysis is hard, and maintaining these tools is a lot of fun, but also a lot of work. So we welcome any contributions to these frameworks. So by reporting bugs, that's one way to contribute. Fixing bugs, it's even better. If you look into our repositories, you will find some bugs that are flagged with first issue. So that's really something for people to get started with. And of course, we even like it better if people contribute entire features or extensions of Phasar and Soot. And eventually, if you like, you are also most welcome to become a committer. So this is not a closed shop. We are welcome to include other people into these projects as well. And that concludes our presentation, and we are most happy to take any questions. Thank you very much.
Thank you very much, Eric and Philip. So with all these exciting developments on the Soot and Phasar side, we already have a couple of questions. You've already answered some of them, well, one of them at least. So let me just stop screen sharing so that we can see you all and give you the opportunity to now live answer some of the remaining questions. First off, we have Yitzhak Mandelbaum from Google who asks, do you know any applications of Phasar to suggesting fixes? For example, could there be a reasonable integration with Clang Tidy to suggest fixes for problematic C++ code?
As far as I know, Clang Tidy operates on the abstract syntax tree. This is a piece of information that we do not directly have within Phasar. In Phasar, we only have the LLVM IR. But what one could try to combine those two information, so somehow making the AST information also available within Phasar, and then one potentially would be able to combine those useful information, so making use of data flow information to improve the ClangD tool and to provide some fixes or some other issue reportings that can benefit really. Interesting idea. Yeah.
Thank you. Next up, we have a question from, this one's already answered. Then we have one from Anshuman Dulia at IIT Bombay. Do the various analyses in Phasar and Soot have mutually beneficial interactions?
Yeah, that's a good question. So I guess you're kind of asking whether the frameworks are integrating with one another. Right now, they are not. It would be great to be able to do this. But technically, I think it would also be very difficult. Both are quite some beasts, and they don't share the same interfaces right now. So yeah, it's not simple, and we haven't really thought about it very much. We would have to get that somewhat more.
Thank you. Then we have next up Tesla Zhang, Penn State. Do you think it's a good idea to implement the JVM code generation target of some programming language using Soot as a replacement for currently popular tools like ASM?
Wait, I have to parse that again. Implement the code. Oh, so that...
So generate Jimple code instead of generating bytecode for Java with ASM.
Yeah. I'm not sure it would be necessary actually, because so we have a bytecode front end that takes in bytecode and generates Jimple out of it. And that is actually a fairly stable component. So that has been giving us not too much of a headache in recent years. So I'm not sure how much would be gained by actually going directly from the JVM to Jimple instead. I don't think we would gain a lot.
Okay, thank you. The question has been marked by the submitter, I think, as checked off. Very good. Then I have a question from Manas Thakur, who said that the question about a survivor guide has not been answered. That's my mistake. My apologies. Manas asked, first of all, big thanks for being behind Soot. But minor question, is there a Phasar survivor guide for Soot users? So if I know Soot, how to get started with Phasar?
I would probably have a look at the Tucker's paper of 2019. So there you get the general idea on what it does. And also the wiki on GitHub would be quite useful, I guess.
Thank you. Then we have one question from Anshuman Dulia, IIT Bombay. Are there any plans to include analysis specification DSLs to these tools in the near future?
Yeah, so I can say for Soot, we kind of already have this. So for specific purposes, so DSLs, like the name suggests, they are domain specific. And we have a couple of years ago released one tool that is built on top of Soot. This tool is called CogniCrypt. And it's basically an API misuse analyzer that can find any kinds of API misuse, not only restricted to cryptography. And this actually includes an API specification language. So you can write down at a very high level what API users should look like. And then this is automatically translated into actually pretty precise and efficient analysis based on top of Soot. And we are currently teaming up with a few people to do something similar also on top of Phasar. Yes.
Thank you. I guess we can squeeze in one more question, since this is our last session and we'll be running a little late. We'll have some time at the end anyway. I'll take one last question from Manu Sritaran, who asks, UC Riverside, who asks, will next generation Soot still support IR modification and co-generation backends?
We will, but actually, so if you know Soot, then the way it is set up right now, you can basically modify the Jimple IR at any point in time. It's pretty wild. And this has the problem that you cannot do a lot of caching and so on. And in the future Soot, we want to do things differently. So basically, by default, you have a read-only IR, which can be cached, and therefore the static analysis as such is supposed to be rather efficient. But then we will also provide specific APIs to replace individual method bodies and so on. So you can still do it when it's required, but you will do it in a more disciplined way. And that hopefully will give you the control that you need, but it will still give you a pretty efficient static analysis in the first place.
Thank you very much. Then I think you've made very good use of the time that you had. Let me thank you for your talk and your question answers, for the answers to all the questions again. And now let's move on to